Today I'll present two somewhat disjoint works, one on video understanding and the other one on robotics manipulation. The common thread in both is that in the long term, what we really want to do is we don't want to learn from supervised data, but we really want to use as much unsupervised data as possible and learn from the large quantities of data available on the web, but also learn by interacting with the world. Okay, and so first, automatic video understanding. Why do you want to do this? It's quite obvious. So there's large amounts of video available today, and people take more and more videos instead of taking images. You have television, but then you have also YouTube, and you have all the material available on video surveillance cameras, home cameras, and so forth, cars, self-driving cars. And so the goal is really to understand what's going on here. And what is the difficulties here? So in contrast to objects, which are clearly defined and have some kind of limited vocabulary, actions are combinatorial. You can pick up any kind of object. You can perform any actions in combination, in sequence. So there's an open vocabulary. They're often ambiguous. You can have temporal durations. It's not clear how to describe the time. And of course, given that you have this large vocabulary, the human labeling is very time-consuming. And so what we would want to do is to use unlimited training data, for example, on YouTube, see how we can do self-supervision. So for example, just by taking into account the spatial follow-up of the video frames, or to use cross-modal information such as audio and speech, to use self-supervised learning or weakly supervised learning from this data. So the advantage here is that you have this large corpus. In many cases, it comes with some sort of annotation. And so the work which I'm going to present in the following is some of our recent work on learning multimodal temporal representations for video understanding. And so here, the idea is you have the video and you can transcribe the speech with automatic speech recognition, for example, for cooking instruction videos or for general instruction videos. And what you have there is that you have quite a good description of what's going on. So people in general, when they cook, you have many of these cooking videos and people say roughly what they're doing. It's not a one-to-one correspondence, but it gives an idea what's going on. And similarly, how-to videos, again, people are repairing things and they're at the same time explaining what they're doing. And so if you use automatic speech recognition, which is not perfect, but has reasonably good quality, you can really understand what's going on in the videos. And then the second thing which we use here is rely on the BERT model, which has shown to give very good results for natural language processing. I'll go into details a bit to explain the model. And then we show that we can apply it to training data, to training sources for which we have enough training data. So here, for example, cooking and how-to videos. Okay, and just to give you an idea of the pre-training data, so you have all these cooking videos on YouTube. And if you look at the ASR, you can really see that people do say what they're doing, and this gives you an idea of how people are performing these actions. And the second thing we're building up on is the BERT model. So the BERT model, I don't know if you're familiar with it, has shown state-of-the-art performance in natural language processing. So basically, it is encoding, it's learning sentence representations by combining the transformer model, which learns the context for the word features, and technique based on masking to learn the representation. And so basically the masking is done by masking out individual words as a loss function, and next sentence prediction by having two sentences together. And the network is a set of stack transformer, which basically models how the words, the correlation between the words basically. So you can either learn the correlation between words without any spatial positioning, or then you can add to the input the sentence embedding and the position information. To see that on the right, you can add the position information, and this gives you also some structure of the sentence, and then basically you learn how these sentences are represented. And it's kind of surprising, you go away from all these natural language understanding models where you model the syntax precisely, but you just model this correlation, and then you can show that this model gives state-of-the-art performance for a whole set of different tasks. And so here the idea was to take this model and adapt it to video. And so here, what do we have? We have two components. The first one is our video BERT model takes as input at the same time the sentence and the video, and then learns the correlation between the sentence and the video. And then we can train it in a similar way by masking out the video and the language simultaneously. And so what is missing for the video here is you need a video representation, obviously, and some tokenization. So basically in language, the representation is clear. Your model, you have the model is just the sentence described by a dictionary of 30,000 words. And so here we do something similar by tokenizing the video features, by clustering. And then what's the video representation? So the video representation builds up on state-of-the-art 3D convolutional features. So what you do is you take 1.5 seconds of video chunks, and for this 1.5 seconds, you extract these C3D or S3D features, which captures spatial temporal features. It's the same thing as convolutions, but the convolutions here are in 3D, and so they capture, let's say, some sort of low-level information in the video. And then once you have that, we take the pre-ultimate layer, and that's a 1024-dimensional feature vector, which characterizes each of the video chunks separately, okay? And so you have that, then you have these features, and then you cluster them together with hierarchical K-means. We found that hierarchical K-means gave slightly better results than just K-means. And you can see here what you get. The centroids, they kind of represent the different components of the video. So it's similar to what people used for the bag of words. You get this similar discriminative clusters. And then once you have that, you can train the BERT model on this, 300,000 videos jointly. And then possible applications. So here a few examples. So here you can use the model to retrieve possible futures. So you have the encoding for one chunk, and then you can see what would be possible follow-up chunks in this BERT model. Or another, and you can see here, for example, for making cake, the next steps would be putting the cake in the oven, putting some cream on it, and then on the bottom, again, you just like put the things together. And then another application would be to use that to take as input as a language and predict the future visual tokens. And given that this looks nice, but it's hard to evaluate, we evaluated the model for the zero-shot action classification task. And so here what we do is we have the video and the language. In the language we have a standard sentence. Now let me show how to mask the mask. And so what we want to do is to predict the verb and the noun. And you can see here examples. The top, we have the three verbs predicted, which is make, assemble, prepare. 3 verbs with the highest probability. And the top nouns would be pizza, sauce, pasta. And then on the bottom, make, do, pour, cocktail, drink, glass. And so what's nice here, so obviously that looks good, but what's nice here is we can actually evaluate this on the UCOOK2 dataset. So the UCOOK2 dataset is a state-of-the-art dataset for which we have the verbs and the objects annotated. So we have the top 5 verbs and objects annotated, and basically you can then see how this BERT model compares to a fully supervised model. So basically here you can see that if you train, so UCOOK2 comes with a training and a test set, and if you train it on the training set on this S3D, this 3D convolutional features, in the top row we can see that you get 46 and 30 for the verbs and objects as accuracy, top 5 accuracy. Then you can see if you just use a general language model, obviously the performance is low because you haven't trained it on anything. Similar if you just learn the language part of the BERT model, again, it's low. But then if you look at the performance of our video BERT model, it's on par or even a little bit better for objects. So you can really see that by training on this fully weakly supervised corpus and evaluating on some state-of-the-art data set, you actually perform on par with something which is fully supervised, right? And this kind of shows that basically in this 300,000 videos, you have all the information necessary to train a good classifier, basically. And then what's also interesting is to see that by increasing the size, by evaluating the impact of the pre-training size, you can see that by increasing the size of the pre-training data set, you improve the performance. You can really see that by having this large corpus, you improve the performance. And I guess in this case, you really learn these correlations better. And this is something which is known also from language, that you need very large quantities of data to be able to train this approach. And then another evaluation is for image captioning, so video captioning. So again, this is something you can learn here in a weekly supervised way. It's how to perform the image captioning. I'll skip over the numbers because they're kind of not so meaningful. And then we tried something else. We tried to use it also for classification. So we thought it would be nice if we could just use the temporal aspect and the clustering for video classification. And then here actually we saw that the performance dropped. And then the question is, why does it drop? It drops actually because the clustering here is not a good way of presenting the video, right? So by doing the clustering first and then learning the temporal features on top of this, you lose sufficient precision on the feature side to be able to cluster correctly. So you can see then basically the clusters are not good enough. So here you can see different clusters which are assigned, different features which are assigned to the same cluster. And then the question was, what do we do next? So here, if you look at the bird model, what we have this fixed vocabulary. What you really need to get rid of is we need to get rid of this vocabulary, right? It's nice for training, but basically if you want to really learn the features, you need to get rid of the vocabulary and operate on the features directly. So one of the problems is obviously space, right? Because basically if you want to learn the features and the transformer together, you have the space problem. So the first thing was we separated the language model and the visual model in two parts, because then basically it's easier to handle. Then you can use the pre-trained language model. You only have to train the visual model. And second contribution, instead of having a loss based on the clustering, what we do is we have the loss directly based on the features. So as input, we now have the features and no longer the clusters. And then as the measure for masking, we're not masking out the different clusters, but we take as a comparison, the comparison between the masked out features. So the predict fit features, which would be similar to the masked out feature, and basically measure then the distance. So obviously, if we don't want to learn the features at the same time, you can just use the L2 distance, propagate the transformer. But if you also want to learn the feature representation, what we do here is we use contrastive loss, right? So basically L2 loss would be just we measure the difference between the two features. The contrastive loss, the trick which people often use is actually what we do is we have the positive example, but it should be also different from negative examples, right? So there we have to sample a lot of negative examples and then measure the difference. And then basically as a difference to contrastive predictive encoding, we use this bidirectional transformer and the transformer instead of RNNs. And so here, just then on top of this, okay, this was the first thing, and then on top of this, instead of training the model jointly, which is too heavy, what we do is we separate it in two parts. The bird model is pre-trained on the language, and the visual model can be trained in parallel. And then we have the cross-model transformer on top of this, so we can first initialize the visual part, put the cross-model transformer on top, and then optimize the alignment between the two, and this gives us this weekly supervised information. And then so here just the cost. So again, what we do for learning the alignment between video and ASR. Obviously, we don't have a precise alignment between the language and each token. We just have a rough alignment between the sentence and the video. And so then again, we use this contrastive loss to have positive and negative video examples. And then in the end, the overall objective would be the vision part of the model, the language part, and then the mapping from video to ASR. And then if you look at the results on action anticipation, on action classification, so there's different state-of-the-art data sets around. So here now we have pre-trained the model on how to 1 million. And basically here what we have, we look at the inputs up to 1 second before the actual action, and then we predict the action which comes afterwards, right? So what you can see here, these are different state-of-the-art data sets, breakfast, salad, and ActivityNet. What we can see in the different rows, the different time intervals which you use to predict the following action, right? And if you look at average pooling, the window is smaller or bigger, it doesn't make a difference, it's just averaged out, so it has no impact. Then if you look at STMs, you can see that this improves the performance. So by having the model, the action predicts before predicting the action, improve the performance. And then if you use our contrastive coding model, you can see that it further improves the performance. And what's nice here is that really by increasing the time span, we have a significant gain. So it would be 72 seconds before. So we do manage to model the information of a relatively long temporal range. And then similar for the other data sets, in all cases, we have a significant improvement by increasing the time range, and we have a significant improvement over traditional methods. And then what's also interesting here again is to see the impact of the data set size. So here it's the percentage of the full data set. We can see that if you use 100%, it's significantly better than if you only use 10%. And what we can also see is by adding the cross-modal objective, we further increase the performance, right? So basically it means that if you have the cross-modal objective, here we only use the temporal features, but the temporal features get better because it can be used as additional information to learn these features, right? The same thing for self-supervised feature learning. If you have noisy labels, you can use that as information to get better features. And here similar, if you have these noisy labels, you can get a better representation of the temporal interval. And then we also did a study, an ablation study, to see what are the best parameters. And actually what we can see here is that the parameters for the visual features are significantly lower than for language. So for language, the number of layers go up to 32, and the attention heads are also higher than 4. And here we can see that actually the best performance are obtained for 2 or 4 layers and 4 attention heads. So the networks are significantly smaller, and this again is very useful because then basically you can fit the whole information into memory. And so one explanation why it's smaller, it's maybe because we have A, less data, and B, we have this continuous semi-pre-trained features, right? So basically it's more information than for the language features, but it's kind of open for discussion why it's smaller. Maybe it's kind of still something where the data is not in adequacy with the model. But anyway, so it's nice because we can train it better. And then we have also investigated if we can use this for completely self-supervised feature learning. So far it was just pre-training and then using it for a task, a predefined task in computer vision. And then the question was, can we also use it for self-supervised feature learning? So here we just use kinetics to be comparable of the state of the art. So what people do, they take the kinetics videos and use some way or the other to completely learn these features self-supervisedly. So basically just take the video information and then learn the features. And so the simplest way is self-supervised learning by rotation. So what you do is you turn the video and predict the angle. This is like the simplest way for images or videos to do self-supervised learning. So you don't need any labels whatsoever. You just have this information of turning, and then you get this out. Other ways is like shuffling the frames, jigsaw puzzling, and things like that. And so here what we do is we fine-tune. So then we use our S3D features, and we use this contrastive coding model with the transformer as an additional constraint during the self-supervision. And then we can compare it to the state of the art with similar models. Okay, and so what we do here, we can see that basically you have different variants, state of the art. So one would be just maybe look at the column random, so frozen. So basically frozen means that you don't fine-tune the features, you just learn the features and then apply it to a task. So you just train the final linear classifier. What you can see here, the first row would be random, and then the next one is one of the state-of-the-art methods, which is shuffle and learn, and then rotation, and then our model. As you can actually see that, interesting enough, this rotation gives quite good results compared to random or other state-of-the-art methods. And then you can see that our approach improves the performance. So it builds up, it uses the rotation as initialization. If you train it from scratch, it's harder to train. So basically using the rotation as initialization gives better results. But then really having this temporal constraint on top improves the performance. And we're now experimenting with adding also the weak supervision, which helps you to further improve the performance, right? So basically, so this is kind of the self-supervised learning. And then basically, obviously, if you fine-tune, you can also see that you have an improvement. But I find this fine-tuning experiment less relevant because by doing very good fine-tuning, you can in many cases achieve quite almost state-of-the-art performance, right? So I think what's really interesting is to see if you just take these features and eliminate and evaluate how good they are. And then here, comparison to the state-of-the-art, so you can see that our method outperforms the other state-of-the-art approaches. So really by having this second layer of constraints, we manage to improve the performance. Okay, and so what's nice here, so we have seen that this transformer masked language modeling works for video. We can see that all sorts of self-supervised plus cross-modal information improves the performance. That's really nice because then you can really leverage all the data available which comes with this weak supervised information to improve the performance. Transformer can capture longer temporal relations. So this is one of the open questions in video representation. How do you actually model longer temporal relations, right? And that was actually one of our starting points. So it's pretty clear that LSTMs don't improve that much. So if you have some better architecture, maybe hierarchical, it's very nice that this can improve the performance. And then I guess one thing which we're currently looking at is how to go beyond cooking and instruction videos, right? Because for now, it works well for cooking and instruction videos, but in the long term, you want it to work for any kind of videos. And so one way of doing it is probably going away from the ASR and more going to the metadata and seeing maybe pre-filtering which kind of information you use. Okay, so this was the first part, and then the second part. So basically we have seen here some self-supervision, which is just using video material. And so one of the things I would like to do in the long run is also to do self-supervised learning by interacting with the world. So obviously, if you start doing robotics, it's much harder than you think. So basically just having the robot move around and doing random things by itself, it's not totally trivial. So what we started to do, we started to try to do simple or semi-complex tasks, so putting an object in a bowl or making a breakfast. And so here, what we're doing here, so this approach here is actually combining primitive skills. So the idea is basically to have a hybrid between imitation learning and reinforcement learning. And so imitation learning, what does it as a problem? You have to have a lot of demonstrations, and you cannot go beyond the demonstration. So if it's basically something you haven't seen, it can kind of go off the goal, and it's good at solving short tasks, because if the tasks get longer, it gets harder and harder. And then on the other hand, reinforcement learning, you have the problem of only have a final reward, a sparse reward function. So you need dense reward functions, which sometimes is difficult. It requires reward engineering, and it's sample inefficient. So basically in the beginning, we trained our robot just with RL, and it takes days. Basically, you just train it to pick up the cube. Because basically if you have no constraint on the search space, it's very slow. And so the approach here is to combine RL with skills learned with imitation learning. So behavioral cloning is just like the term for learning from demonstrations. So it's just like simply you have a set of demonstrations either on the real robot or in simulation, and then you can learn a model from this. So there are a bunch of approaches for non-hierarchical approaches where they use imitation, where they combine imitation learning with RL. And then also one or two which combines imitation learning with RL in a hierarchical way. And so what our approach does is we first have a set of these short skills, and then we use RL to define the order of the skills on top of this. And so basically for now, our skills are handcrafted, but in the end of the day, what you really would want is to learn these skills automatically and then train an RL on top of this. And the RL basically is completely automatic, so you can really choose which skills to pick. And then if a skill is not executed correctly, you can repeat it again, right? So I'll start by presenting first the model for the skills, and then I'll present how to put the RL on top of this. Okay, so maybe here. So what the imitation learning does, so here we first learn in simulation and then have an approach how to perform simulation to real. So what we have is we have an input of depth frames. So here it's the 3 past depth frames which we take as input to the neural network. And what we want to predict is the action of the robot. You want to get the angular and linear velocity, so V and W, and the state of the gripper. And so this is the input and the output. And so basically once we have this gives us the control policy. Given an input of 3 frames, what is the next action the robot is supposed to perform? And the loss we minimize here is then basically the loss, the L2 loss on the angular velocity constraints and the open and closeness of the gripper. And then the network which we train, so here again our depth input, we have a CNN which is trained jointly for all the different skills and the master policy together. What we found important in practice is to have this one hot vector encoding to tell the network in which state you are, so which skill you're actually currently looking at. And then basically you have the different heads which predict you the policy of the skill. Basically, you know you're in skill 1, and then you say, now, given the skill 1 and the input, you get this output joint configuration. And so I guess if you don't have this one hot encoding, it starts mixing up the policies together. So that was in practice very important. And the second thing, get back to this, is important. Same conclusion as for vision, that if the network is too simple, not deep enough, then the results are also significantly worse. And then once we have that, we have the skill policies in parallel, and the master policy can be then also use the CNN and is then trained once we have the skills pre-trained. Okay, here, and then basically what we found important is the number of expert demonstrations. So that's basically the thing. If you learn from these demonstrations, you have to have a significant number. We found that it's important to have them recorded from a set of different viewpoints. That's to be invariant to the camera, to small changes of the camera position. And then basically the architecture. So basically we found that using ResNet 18 gave good compromise between accuracy and speed, so similar to what people see for images. And so here, basically, first thing, if you have a network which is not powerful enough, so for example, VGG, we can see that by having ResNet, the performance is significantly better, especially if you have enough demonstrations. We can see that the performance improves for more demonstrations. And then similarly to what you see in images, also data augmentation gives significant improvement in performance. So by having standard data augmentation, you can see here, you actually go from, if you have 50 demonstrations, you go from 5% to 80%. So it's really important to have this data augmentation. So really similar to what you would have in standard computer vision. And then the viewpoint data augmentation further improves the performance. And if you combine the two together, you get good results. And then basically here, this is trained only this tested only in simulation. So I think the viewpoint augmentation, if you go from simulation to real, is more important still, because often in practice the camera position changes slightly, and that's kind of one of the problems with these learning-based approaches. And then once you have this learned in simulation, so for now, obviously you could also train on the real robot, but basically that's only possible if you have a robot which really runs all the time. And so what we did, we trained in simulation and then have an approach which goes from simulation to real. And so several of the state-of-the-art approaches, what they do is they learn how to augment the data in simulation. And then once you have augmented it sufficiently, you can just run it on the real robot. And so what we found in practice is actually the robot arm can be modeled quite precisely. So the robot arm is quite repeatable, and the problem is really the vision part, right? So basically the vision part changes. If you have lightning changes, for example, then the depth camera gives slightly different responses. So it's actually important to augment the data, and once you have augmented the data sufficiently, you can just then do sim to real. And it works surprisingly well, I would say. And then here, what do we use for data augmentation? So what we have one data point in the real world which we use as measurement. So we have the cube, we have a cube in the real world. And what we do is we use the augmented model to predict the cube position. So we have this cube, the image, and the cube position, which we use as the error. And then what we do is we have this whole set of augmentation. So you can see here, salt and pepper, noise on the borders, cropping, pasting in wrong objects. And then what we do is we have a multicolored tree search algorithm to find the best way of augmenting the data. And so basically, if you augment with this pre-trained set of transformations, we can show that this improves the performance significantly. Okay, so here we have this one error to find the optimal sequence of augmentations with multicolored tree search. And this gives you, we can show that this gives better results than just randomly picking any way of doing the data augmentation. And then obviously it's important what kind of base transformations you have. And so here you can see what the transformations which we use. So here we can have scale change, salt and pepper, here, top cutout. So we cut out objects from the image, erase an object, white noise. Edge noise is quite important because that's kind of something which appears very often in the real world. And then scale, salt and pepper noise, posteriorized sharpness. And okay, this is then And then we can show it once we have augmented the skills. I'll show the experiments later. We can see that having this augmentation, we can then run our policy trained on sim on the real robot. And then the next thing is once we have the skills, how do we train the master policy on top? So what we want the master policy to do. So we have this set of skills. For now, our skills are hand engineered. We could obviously just decide ourselves how to put them in order, right? We could just say we know the skills, we know what the sequence is, we put them in order. So this is like one of our baselines. I'll show that the RL works better. And what does the RL do? Obviously, it decides the order of the skills automatically. So if you have a new task, potentially you can use it to discover what's the order of the skills for the new task. And second, it learns how to switch between the skills more appropriately, right? If you just put them one after each other, you can run them for a certain time step, finish, and then go on. And the RL, what it has, it checks if it's done, and it can repeat the action over n times, several times. So if there's a failure, it can repeat the action again. So it's more flexible. And so here, what we do, we use the proximal policy optimization to learn, so it's a state-of-the-art algorithm to learn the master policy. So this is actually something we're currently also looking into. What is the best way for learning this master policy? Is it better? Are there better methods? Is it better, for example, to do residual RL to learn just the RL on top of the learn demonstrations? And so the experiments which we're doing are on two tasks. We have two tasks, Euro 5 bowl. So we pick up the cube and put it into a bowl. And then Euro 5 breakfast, where we model, where we have two different, a cup and a bottle. We have to pour the ingredients from the cup and the bottle into the bowl. This is like the first step towards making a breakfast or making a meal. And you can see here on the left is synthetic data, and on the right, the real robot. So basically we have a model of our robot arm in the synthetic data. And so here, the different skills. So we have go to the cube, go down, grasp, lift the cube, go to the bowl. And similarly for the salad, so the salad just go to the cup, go to the object, and then once we are at the object, we grasp an object and pour and release the object. And so one thing which is important, after having performed the pouring, we have to put the object out of the side of the view, because if you just leave it in the side of view, the robot will just grasp it again, right? So basically there's no memory in the real algorithm, so once it sees the object, it just pours it again and again. It's actually quite surprising how it doesn't have any memory, right? At least for now. This is like something also to be checked. And so here, a small video of what our robot does. So here in simulation, not in real, so go to the cube, you can see the different skills which are executed on the top. And here you can see which are the components which are active in the neural network, right? You can see which of the neurons fire, and you can actually see, as you would expect, it fires on the object, right? And it indicates where to go to. So yeah, and here you can see that the approach is robust, right? So basically, given that you have the RL, which acts as like a controller, and then the image input, which is adapted in real time, you can really see that the robot manages to adapt to the approach. Then similarly, if you have occlusions, again, while it's occluded, it doesn't see anything, doesn't do anything, you take away the object, it can react again. And then it's a CNN, so basically it can generalize previously unseen objects. So what it has seen so far is just a cube, and then here basically can also grasp other objects which are kind of similar, right? So basically what the environment stays the same, and then basically the object is kind of a cube or an object. And then I guess one thing is that grasping is quite easy, right, as a motion. Basically, once you go down to the object, you can, anyway, it generalizes well, but it's kind of, it explains why it works. So if you see the object you detect, you go down and you close the gripper and it still works. And this is the thing with the RL, right? If it hasn't executed the policy, it can do it again and again. So this is the loop, right? If you have the RL, it kind of goes, during n time steps, it performs the skill, and then if it hasn't been done correctly, it verifies the condition and then goes there again. And then here, making the salad and not making the breakfast, it's slightly harder. There's these two objects, and what we found, it's much harder to do the pouring, right? There you have to turn the robot arm, and it makes a big difference, the type of motion the robot is performing. So if you just grasp, it's much easier than if you want to do an action like pouring, or maybe cutting. One of the things I want to do next is cutting, but it's significantly harder. And then when failure mode so BC ordered is like just ordering the skills. And so basically there you have no flexibility in the approach, and then it just throws over the ball. And then if you look at a systematic evaluation of these different perturbations, so basically no perturbation. So these are different baselines. Detect and plan is just you would detect the object and then use inverse kinematics to go there directly. Detect and replan is you have just a simple controller on top of it that basically if the object moves, you can redetect it and replan. BC ordered would be taking our skills as input and ordering them, putting them in the correct order. And then RLBC would be our approach. And you see, if there's no perturbation, they perform roughly similar. If you move the object, detect and plan doesn't manage to get it at all. Replan kind of also does manage to get it once in a while, but it doesn't perform as well as our approach. And then BC ordered, again, it has some problems. So if it doesn't manage to get it first, then you don't have the control on top of it. And then similar for inclusions. And if you have new objects, also it's not as robust. And then here, if you measure the amount of position changes, again, our approach is more robust than the three baselines. And similarly for the amount of occlusions. So if you have more and more occlusions, the performance for the state-of-the-art methods goes down, and our approach stays at the 100%. And then here, again, new objects, you can see that all approaches are quite robust because they all use CNNs as input, so they're all quite robust against new object instances. And then last one is the distance between the bottle and the cup. So if the bottle and the cup, they're too close, the ordered skills don't work anymore because it doesn't manage to kind of adapt the plan based on the order. And so in conclusion, we have seen that Sim2Real is efficient for data augmentation, in particular for depth information. We're currently looking at how to augment also RGB, which is obviously harder because there's a much larger domain gap. And we have seen that the vision, that architecture and data augmentation are important. So that's basically improving the vision side of things, right? So there's nothing magic here. It's just that basically once you have a better algorithm for the vision problem, the whole architecture improves. And so that's really not improving that much the robot controller, but it's just like improving the recognition of the vision side. We've also seen that picking is relatively simple and pouring is significantly more complex. And then next things would be automatic skill discovery and also speed of simulation, and then more complex grasps. And so basically here, it's still relatively simple. In the long term, what you would want is like more complex actions, and in particular also learn the skills. And then one thing is to go from video. Ideally, you would just go from video to the real robot, to show some video of cooking, and then the robot manages to cook. So long-term goal, kind of hard, but. And then the other thing which we're looking at is language to action via vision. So what you would want, again, is just to give the robot an instruction, and then the robot just executes. Since you don't have to show any examples, you could just say, take this bowl and put the cube into the bowl, or just cook me the salad, and the steps are the following, and then the robot would do this, and it can be formulated. We've started to look at it as a translation problem, right? So the translation is not from language to language, but it's really from language to the actions via the vision component. And then, as I said before, in the long term, what I would want to do is to use this for self-supervised learning. So basically to see if the robot, by interacting with the world, can learn better features or better skills. And so there's, for example, the work Learn to Play, which kind of learns how to explore the world. There may be one thing is that we might need better robots. Okay, and I had the last part, which is like learning how to learn visual categories, plans for visual categories automatically by disassembly. But I think I'm just at 40 minutes, so I just give a brief overview. So what we do here is instead of learning things from simulation, the idea here is just to have the robot, either in simulation or the real world, disassemble the object, and by disassembling the object, you actually can revert the plan and learning how to assemble. So this is definitely not the solution for everything, but it's like an initial idea, maybe how you can do this automatically, right? So that you don't have to construct in simulation the full plan of how to put together an object, but you can learn by disassembling. Actually, it does work, and it's quite nice because it's kind of an idea. Probably humans learn by disassembling or by interacting with the world, and this goes into the first step into the direction of self-supervised learning. Okay, thank you for your attention.
Thank you very much. Questions?
Well, does robot observes the level of liquid while it pours water? Or
Does robot?
Does robot observes level of liquid while pouring water?
Well, it observes how the balls fall into the bowl, right? So yes, so the camera, so what we have is the camera's not on the arm, the camera is like in front of the robot, and so you can actually see how the balls fall into the bowl, right? So you can potentially detect that they're all in there, so you can see the level. So you can measure if it's full or not. I mean, this is just like a vision problem which you can solve, so yes.
And how it finds similarity between small objects? Is it with correlation of this bigger thing? Where
you mean between the frog and the cube?
Yes.
So I guess this is just a neural network, right? So basically a neural network, if you train it in, so the environment is the same, right? So the environment doesn't change. So it's trained on like objects on a table. And then I guess if you learn how to detect a cube, I mean, if you just think of an object proposal network, you can say there's a cube there or there's a ball there. And so basically this is just like standard vision, right? Vision convolution network has some power of generalization, right? And this is kind of what we're building on here.
No, does it compare only embeddings of these images, or you have classification of?
So what it just takes as input the ConvNet and outputs the action of the robot, right? But basically, if you look at what it does, if you look at the interior, it highlights the neuron highlight up on the object. And if you think of an object proposal network, you would train object proposal on the cube. It would also find objectness on other similar objects, right? And so basically, it looks surprising, but it's actually the capacity of a neural network which you use here. And as you see, basically, even for frogs, it works, which is nice. And then basically, once you have that, the gripper has similar positions, right? So it wouldn't work maybe for other more complex motions where you have to have a much more precise grasp. But here, if you just want to grasp, what you do is you go down and you close the gripper, and that's good enough, right? Once you have the position, then you go down and you grasp it, and that's the same. And the height of the table stays the same, right? So it's not changing. And they are roughly the same height, right? That counts as well. If they would be much higher, maybe then it wouldn't be able to grasp it, right? So.
Thank you very much.
Thank you. Any other questions? Oops.
So thank you for the very nice talk. So in the second part of the talk, you have this notion of skills that need to be currently manually defined, right? And to some degree, they make me think of the dictionary that you had in the first part of the talk, which we eventually got rid of. So do you think there would be a way of going to not having to define explicit, discrete skills, but have a more continuous representation?
Good question. But then if it's completely continuous, then you would be back to the RL part, right? And you would just learn totally without initialization. I guess what you could do is have some kind of hybrid system, maybe where you have some sort of initialization and then have the continuous learning, right? But here the idea is really to have this decomposition. And so we did try a hierarchy of RL algorithms. So that would be maybe the most similar reply to what you were saying, and that was also quite painful. I mean, the optimization is quite painful. So the question is like, maybe you can have, as we did in the first talk as well, right? We had this rotation invariant features as initialization. So maybe we could have some initialization. Actually, it's maybe a good idea. We could have some initialization and then put learn the continuous approach on top of it. Because if you just train without initialization, it's maybe too hard. And the second thing I think, which we could learn from the first part, is to have a better temporal encoding, right? So now we just stack these 3 frames together, which is completely suboptimal because we don't model at all the trajectory. And so there, if you have some better model of the temporal representation, it could definitely help.
And so, sort of following up on this, but more focusing on the first part of the talk, you went from the discrete dictionary for images to a sort of continuous representation. For the speech, of course, for speech we have a natural dictionary, but then you could also go to a continuous representation to encode the entire soundtrack, not just speech. Do you think that would make sense? Do you think that would make it easier to use more videos that are not instructional videos?
You mean instead of doing the ASR, just use the speech as input?
Use the
and
full
then
sound, yeah. Well, yeah.
Use the full sound as the correlation? I mean, I don't know. For speech, I'm not so sure because there the ASR is a very good proxy for encoding the speech. And I think people have, I mean, I've seen people experimenting with the audio instead of like the transcribed speech, and there I didn't see that much, or it was actually worse because somehow, I mean, it's just a very good thing, a very good tool, right? And it works very well. And so you're kind of throwing away information which you have for free. But what you can do, and what I've seen, what people have been doing, is to use the audio in case there's no speech, right? So for example, there's this Epic Kitchen video, and I just talked to somebody, and you have the sounds, whatever, like of frying and things like that. And that's like that can be used as an additional source of information. So ideally, you could maybe separate it into speech and then non-speech, and then use the audio as an additional descriptor, right? Because that's really characteristic. While for the speech, I think, I mean, what would you gain by not putting it into the speech? I think you would, I mean, there are a few mistakes, but the mistakes are not major. So I think that's not an argument. The only thing you could get is like that you have the different voices or something which might change. So if you want to do speaker identification, maybe that could come out automatically, but that's not there because we're not having the phases and we're not having the speakers separated. But so I would say for now, no.
Okay. Yeah. Thanks.
Any other questions? Okay, really, you just gave me nightmares of my robot watching TV and then learning to do what is on TV. Like your last slide when you said that the robot's going to learn by video. But actually, it's a serious question. Wouldn't you need to have 3D information for the robot to learn from a video? Or do you think that after a while you'll be able to basically restrict the physical world or put a model of the physical world that one could learn from a video to actually do some 3D movement afterwards for a robot?
Yeah, I think you can actually, I mean, basically video is in general 2D, right? So
Right,
then the
exactly.
question is, how do you go from this 2D information to the 3D? And so I guess one thing we're currently looking at is how to get 3D information out of the video, right? And so basically the question is, can you go directly from 2D to 3D by just watching this? Or do you have to have some kind of intermediate 3D representation, which then transfers to the robot? And it's clear that if you have the 3D information, it's much easier, right? For example, there's this work from Berkeley where they have these humans reconstructed and then they go to RL, and that's kind of where the 3D really helps because then you can do the RL directly, while if you would just go from the video to 3D, it's harder. But then on the other hand, we have seen also that sometimes intermediate representations, if you have clever enough training data and setting, then you can get rid of it. So I don't know if you need these intermediate representations or not, but obviously it makes it easier. And I think one of the things which are actually interesting to look at is how much 3D helps for the robotics problem, right? Because now most people, they don't use any 3D, and there's a lot of information like in computer vision about this 3D information, which obviously if you have, I mean, it starts with camera calibration, 3D reconstruction, having a stereo camera and things like that. And if you have this 3D information, it's pretty clear that you can have some additional information. I think this is one of the things, or even from a single view, you can get some sort of 3D reconstruction, which you can then use to get a better representation of the robot. In particular, maybe say if you want to have the obvious grasp point. So I think it's kind of one of the open questions is how much 3D helps. The same thing for action recognition, right? It's something which I've looked in several times, and in the past it didn't help much, but I think the 3D reconstruction was not good enough, right? So basically, if the 3D reconstruction is bad, then you lose so much information. I mean, similar to the speech, right? You lose so much information before going to your goal that it's not working. But in the long term, I think at least having some sort of notion of 3D is definitely something which we want. And I think we'll be getting there because now there are approaches where you can go from video or even Englishes to 3D, right? And so that's definitely something to be checked out. And I'm sorry, I'm giving you nightmares about the robot
I'm
watching.
just teasing, right? I'm just seeing my you know, my little robot that cleans the carpet starting to watch TV. No, I'm just kidding.
Yeah, but then if he cleans better or...
That's true. Okay, thanks very much for an interesting talk.